from from whatever data has been acquired from hardware. Okay, it will be able to process it in real time as well. Okay, so right now if you see most of the data from system what we saw, okay, they are like not really movable. Okay, so this is very heavy equipment. It's not like very heavy equipment that an automotive system cannot carry. Okay, but this should be directly having a Windows system. Okay, and this will be processing it. Sometimes we need to have a rugged as well as less weight equipment which can go inside the automotive system itself. So for that we'll use something called as compact trio systems. Okay, and compact trio systems are basically programmable using LabVIEW directly. Okay, so that's an embedded system which can be programmed by using LabVIEW and operated by and monitored by using LabVIEW. So that can also be done, okay, in the LabVIEW itself. Okay, so we have LabVIEW project, okay, which can help us log data inside. So since LabVIEW is not it's used for scientists and engineers, since when scientists and engineers will be doing projects in a very soon manner, okay, so since they'll be doing it in a very fast manner, they need to have templates, and they'll be having a lot of templates with respect to data updates and stuff. So if you see, when I have a compact trio, okay, I have a compact trio simulation. Okay, if I have motor simulation, I have motor simulation. Okay, so for everything there will be a sample project available with which you can expand your application to more needs. So compact trio, as I told you, is an embedded system. Okay, and this embedded system can be used for acquiring data in real time. Okay, on board an automotive system, and it can be logged inside compact trio. And that data can be logged into one type of file, some type of file, and that data can be processed, okay, by using your computer. After you bring it into, let's say, like a file like this, okay, it can be processed according to your own needs, okay, like calculating the charge, calculating the energy. After calculating this, let's say if you want to find the state of the charge and state of the health by available technique, you can proceed to do it. Okay, so there are ample opportunities which you can execute using LabVIEW that case. Okay, so you can either you do a fixed calculation, like you would already know what is the capacity of battery divided by that value, or based on certain parameters, you can calculate the state of charge. Okay, that will be equation development. Okay, that will be done by you. Okay, so we have just told you that this is the path which you can go. Right. So, which company has done it? Okay, which company has used these things and did? We'll see an example of one of the case studies. Okay, so okay, they made a cyber secure control system. Okay, without ability to getting hacked. Okay, they were making for a zinc bromide battery. Okay, different batteries in a format. For this, they used a compact trio, LabVIEW, and they basically used this. This is the battery. Inside the battery, okay, they'll be having the compact trio module, which will monitor and control the battery management state. And this is the flow chart of the zinc bromide battery. Okay, internally they'll be having the signal conditioning unit as well as the signal, okay, which will be acquired from the battery. They'll be converted to something your compact trio can read, and once it is read, it will be processed inside the compact trio itself. Okay, and the compact trio will basically transmit data from this battery potential to other batteries by using something called controller alienator, that is CAN. Normally, CAN will be used in automotive systems, but it's not like you have to use it only in compact trio systems. Okay, so 4 batteries will be individual batteries being monitored by individual battery management system. Okay, so battery management system is basically embedded system. Okay, it could be it could be a normal ASIC chip, or in this case, it's a separate embedded system which does not only have acquiring data and processing capabilities, it also has communication capabilities. Okay, basically CAN protocol is implemented, and you have one more master BMS. Okay, these are all slaves. Okay, for individual things you have individual slaves, and every slave will communicate to a master BMS. Okay, and this master will have one more multiple separate master. Okay, these masters also will communicate, okay, through Ethernet, okay, or CAN, right? And this will be communicated to an energy management system. Okay, and the energy management system will be communicated via cloud. Okay, so you can have one more software setup called as performance tracking. Okay, so through that you can just tell, okay, plot this energy path. Okay, so you can set up. They have set up all these things by using LabVIEW and a couple of other partners who provided the circuits. Okay, but data acquisition was provided by LabVIEW. Okay, other things like charging, discharging, everything is controlled by using LabVIEW. Okay, so you have charging, discharging, sensors, actuators, state of the charge calculation. Okay, it is being done by the hardware. Okay, so not only in the industry they use, let's say you want to do academic project. Okay, so academic project like research project as well as student project. Okay, so this is one more case study. Okay, which was done by one university in Spain. Okay, so they basically did a total battery management system using a hardware called as MIRI. Okay, so using this MIRI is also programmable by using LabVIEW only. Okay, using this LabVIEW will acquire data from the appropriate sensors, voltage, current, temperature, and they were able to implement. Students were able to implement the BM. Okay, on lithium ion cells. Okay, and they were able to do it in short time because LabVIEW is synthetic programming experience. Okay, so it was a university called as Mondragon University. Okay, it's in Spain. Okay, so basically they used LabVIEW, MIRI, and the protocol which is followed by the software, instead of using MIRI for as a end terminal system, okay, they use a battery management IC. Okay, and the main battery management system is your MIRI. Okay, so slaves was this ASIC chip called as LTC6821. Okay, which will monitor the battery. Okay, so basically this modular hybrid BMS the thing was topology was used. Okay, basically they used something like this. Okay, different voltages from different cells was monitored by the single IC. Okay, and all this was connected by using the SPI bus. Okay, and using the SPI bus, they were able to send the data of individual IC, okay, to the BMS master. Okay, so individual cells were being monitored by individual LTC IC, and it was communicated to MIRI. And whatever data needs to be viewed, okay, and controlled, they were done by using LabVIEW. The LabVIEW is running internally inside the MIRI. Right, so the setup was something like this. Okay, you have the lithium-ion battery. Okay, from that individual IC, they connected to this BMS chip. So that is the slave chip, and the slave chip is connected to your SPI bus of your MIRI, and it's getting monitored. And using this particular IC, the particular BMS, they were able to use this battery and the battery management system in an energy efficient manner into secondary applications. Okay, they developed applications based on this battery for battery test system. Okay, which is and ovens and heaters to use inside the research. Okay, voltage sources for different experiments, and electronic charge generators, spectrometers, impedance meters, etc. Okay, so using this, they were able to efficiently make use of the application. So key takeaway here is implementing a BMS for lithium-ion cells. Okay, using in a very short time, because time to market nowadays is very, very small. not experience quick development environment. Due to development, okay, program development, your application should not be stalled. Okay, and you can develop a lab front panel, okay, which will intuitively view all the parameters, okay, in real time and giving constant on controls and stuff. Okay, and you can also create an alarm. Okay, if some parameters going, you can set limits, okay, very quickly. So with that being said, battery management is done. Okay, next we'll move on to the next phase of your core focus, that is going to be a power inverter. And before that, if you have any questions on this particular topic which I covered, please let me know. Okay, I'll try to answer it, okay, as soon as I can. Or else we'll continue to the next topic. Okay, and once I am done with this introduction, okay, I'll just be doing the introduction. Okay, and the implementation and the special case studies and other things will be covered by my colleagues. Let me know if you have questions. I will see the chart.
So any clarifications, you kindly ask, or otherwise we will continue with the next session.
Okay, fine.
Okay, sir. Thank you.
Yes, in that case, let us move on to the next topic. That is, when we take an electrical vehicle, 3 core components are there, apart from other systems which may also exist, which will exist, sure, for sure. Okay, so the key 3 core components for electrical vehicle to be operating is, first one is battery, a traction battery, which will supply high voltage, high current, etc., etc. Okay, and since it's high voltage and high current, high power will be generated, drawn from it. And in order to monitor and control, okay, we'll be using traction battery, battery management system. Okay, next part is power inverter and controller. Okay, since most of the motors which we use needs to have a control strategy, okay, we need to make use of a certain inverter and controller to convert the power from the battery to something which an electrical motor can accept. Okay, so an intermediate circuit of drives will be used. Okay, we'll be seeing how we can make use of the environment of NI, the software environment and hardware environment of NI, to implement it. So what does NI have in store for us to do this? NI basically supplies tools for in powertronics. Okay, the domain of basically powertrain is a powertrain circuit, high power electronic circuit. Okay, so what does it offer? What does it bring to the table? So first one it does is it does power converter prototyping. Okay, then power converter monitoring and control circuit, or the algorithm behind the control and circuit and monitoring. And next one is electrical machine driven control. Basically, if you have your electrical vehicle, it will have a motor. Okay, so that should be driven by a power converter controller. You'll have a drive, solid state drive. So which should be first prototyped, and after prototyping, a particular control algorithm should be developed to monitor the electrical drive and control. So how does NI operate? What are the main tools available inside it? So basically, if you take power converter prototyping, okay, you'll be taking this. First one is will be having is your battery will be there. The battery will be separately done. The next one is going to be your electrical power drawing circuit. Okay, it could be a 3-phase inverter, or it could be a DC to DC converter, so on and so forth. Okay, so energy storage and energy monitoring system we have already seen. Okay, next one is going to how to prototype, test, validate, and deploy these. Okay, is what we are going to see next. And in order to do this, we may not be directly using only LabVIEW, okay, and the associated hardware, because circuit design is an art, okay, and it needs to have a separate expertise. So even though you have the circuit in hand, before you actually build the circuit, and in order to prevent you from building the faulty circuit, first you should be able to simulate the characteristics of the circuit in a separate software. LabVIEW is totally not used for building circuits. Okay, even though it has front panel, block diagram, terminals, okay, it's used for instrumentation purpose. Okay, and control algorithm development. In order to create mathematical model of the circuit, okay, we do have a separate software called as Multisim. Okay, Multisim will create a mathematical modeling of every circuit, which will be used for simulation purposes. In order to simulate the characteristics of the circuit, we will make use of Multisim. Okay, so basically we'll make use of Multisim to create this circuit. Okay, and the control algorithm on the other hand, for in order to control this inverter or DC-DC converter like PWM generation and other things, will of course be done by LabVIEW. Okay, in LabVIEW will generate these signals. Okay, and not only can you use multisim for circuits, okay, you can also combine the algorithm development, the control algorithm development in LabVIEW, and you can basically combine both multisim and LabVIEW together. Okay, this is something which is new. Okay, so most people will be like, I can use Cadence OrCAD to develop my soft circuit. Okay, and simulate the characteristics in the OrCAD itself. Okay, but here the advantage here is you can use LabVIEW to develop algorithms and send the signals from LabVIEW to multisim, and the response will be brought back to LabVIEW again after it's processed. And the programming you don't do in any scripting, okay, because LabVIEW is just flowchart, so you can just easily combine both of these things together. And you can also build control algorithm like PID, fuzzy logic, neural networks, okay, inside the LabVIEW, okay, and build a closed loop system, okay, using this both combination. So NI's vision for power electronics is basically like any other application development in iteration. First you do design, prototype, and deploy. Okay, so first what we do is when we design itself, we follow V model. It is called V model. Okay, so when we design itself, we'll create testing for design. Okay, we'll test the design very stringently. We'll apply different test cases. Okay, we'll try to simulate different thermal measure temperature. We'll try to measure different frequencies. Okay, everything we'll try to apply scrutinize as much as possible in the design itself. Okay, so as much as possible, we'll try to scrutinize the design. We'll find the flaws. We'll fix it, and then we'll go for prototyping. Okay, so this both will happen hand in hand. So this is called test-driven development. Okay, then we'll go for prototyping. We'll build the circuit. When we build the circuit itself, we'll do something called ATAL testing. Okay, we'll develop the mathematical model of the circuit and we'll deploy it inside the one type of hardware called as HAL. So mathematical model in real time using the computers will not be possible because computer will have own time domain processing. So in order to do it in real time, we'll be having HAL simulation. Okay, whatever signal needs to be given to the circuit will be given to the HAL model, and that will process in real time and it will give it to us. So we'll be sure that okay, this particular circuit, whatever we have developed in computer, is correct. So prototyping and HAL testing will happen, and whatever problems was not found during design will be found during HAL testing and prototyping. And once this HAL testing is done, we'll give you PCB, okay, and we'll scrutinize it as much as possible, and we'll go finally to deployment. And during this process, people may be saying, during design I'll be using one software, during this I'll be using separate software, and during this I'll be using separate software. People will be thinking, okay, but only two softwares will be used. One is LabVIEW, one is Multisim. First of all, one is Multisim. Then after you're done with Multisim, to control the characteristics of the circuit and to program, embedded systems, to program FPGAs, okay, use only one software. The control algorithm, everything will be done only by LabVIEW. So for deployment phase, you'll be having LabVIEW plus hardware, both control as well as measurement. Because during control also you have to measure also. To implement closed loop system, you'll be constantly getting feedback. Okay, so that will also be done using LabVIEW. plus hardware. Okay. So here key applications, there are different types of applications which can be implemented. Okay, you can do grid-tied solar inverters, okay, wind turbine power converters, okay, renewable energy basically, and you can do energy management system, voltage, motor drives and pumps. Okay, and more importantly, electrical and hybrid electrical vehicle, mobile and automobile, trains, industrial agricultural vehicles, okay, systems can be implemented using. Okay, so using this V model. Okay, so that's about it for my session. And other things like how we can use multisim to create circuits, and how we can use LabVIEW to create a control algorithm for it, and what type of circuit can be designed, what type of strategies, those things will be continued by my colleague, okay, who will be joining the session in a few moments. But as far as now, whatever I've done, if you have any questions, please feel free to ask, or if you want to contact me separately, we do have my contact information through which you can contact me, and you can get your doubts clarified. Or if not, so I'll
Thank
just
you, sir.
drop this contact information in my. Yes, thank you, ma'am, and thank you for giving me this opportunity to present my insights on how we can use this. I'll just drop my information in the thing chat. If you have questions, please do ask, or else I can hand over my session to the next person.
Okay, sir. So thank you. Thank you so much for your wonderful presentation, sir. And real-time LabVIEW applications and how to use that software and all, you have explained very well. Thank you so much. And the next, this session is continued by Mr. Eseki Raja. Sir, good
So
morning.
Yeah, good morning, ma'am.
So, good morning. It is my honor of introducing our resource person, Mr. Eseki Raja. In this fourth day of second session of ATAL FDP program, Mr. Eseki Raja graduated as Electrical and Electronics Engineer from Anna University, Chennai. Currently, he is designated as Senior Application Engineer in VI Solutions, Bangalore, certified LabVIEW developer, and handling major responsibility of supporting various industries in implementing several turnkey systems and system integration projects using NI technology. He also took place in deploying research labs in FPGA-based data acquisition and control design, automation, and in machines lab in various institutions. He had conducted more number of hands-on training to engineering students and faculties of various branches on LabVIEW basis and data acquisition in NI embedded platform. He also had conducted many faculty development workshops on various trending technologies, including signal and image processing, PQA and PMU, etc. He has delivered more than 30 lectures on experimental engineering education on varied technology topologies. His key interest areas are sensors, actuators, data acquisition and signal conditioning, NI certification and training expertise, power quality analysis, phase measurement unit, embedded and control, circuit designing using multisim, automated testing equipment. With this very excellent profile, we are very much happy to have you for this session, sir.
Yeah, thank you so much for your warm welcome, ma'am. So,
I welcome you again and I hand over the session to Eseki Raja, sir.
yeah, Thank you so much. Before I'm getting into the session, whether my voice is clear, just give me the confirmation on my audio so that I can proceed with the
Yes, sir. Your
session.
voice is clear.
Yeah, okay, thank you then. So I'll just share my system screen. So, yes. So fine. So we'll get into the session. Okay. So once again, I welcome everyone to this FDP program. Okay. So I'm going to continue from the previous session, like where exactly Raj completed his session. Okay. So yes. So as you all know, so this FDP is regarding the EV, right? So in an EV, if you see the core composition of an EV, right, we can segregate it as a three part, like a power inverter and a converter, then electric traction motor. So among these three core components, I'm going to focus only about this power inverter and converter and electric traction motor. Okay, so these are the two core components I'm going to focus today. Okay, so in this, first we will see what is the role of national instruments when it comes to EV. Okay, so when it comes to NI tool, okay, so in the previous session, Raj has been showing you about a LabVIEW, right? So LabVIEW is not only a tool which can be used for power electronics or irrespective EV. Okay, so there are some other tools, okay, from national instruments which can be used for several applications. Okay, so we are going to work with LabVIEW. Along with that, we'll be working on a multisim. Okay, so multisim is actually a circuit design tool. So we'll be parallelly working on these two softwares. Okay, so apart from that, we have a few more softwares like a test stand, which will be completely meant for testing purpose, like automated test equipment. Okay, and we have a very stand. Okay, so there are a few more tools, but those tools, right, will not come into a picture for today's concept. Okay, so in today's concept we'll be focusing only about two tools. One is LabVIEW and another one is a multisim. Okay, so first we'll see what are the things we are going to do in today's session using these tools. Okay, so first one will be focusing about a power converter prototyping. Okay, so now you might get into a question like why we need an up power converter. Okay, so I'll tell you two scenarios. Okay, so where we'll be using this up power converter. So the first one actually have implemented in one car. Okay, so I forgot the name actually. Uh, in one particular EV, okay, they need 500 voltage output. Okay, they need a 500 voltage output. If they want 500 voltage output, right, in their battery, they need 413 cells. Okay, they need 413 cells to get 500 voltage output. So if they keep 413 voltage, what will happen is the weight of an EV, right, it will get increased, like the electric vehicle, right, it will get increased. So what happens if weight increases, a load for the motor also will increase. So the performance of the motor will obviously it will get decreased. So to overcome this issue, what they have done is they have taken only around 100 plus cells. Okay, so they have taken only instead of 413 cells in a battery, they have taken 100 plus cells. I'm not sure about the proper value. Okay, so they have taken around 100 plus cells, which gives 200 volt. Okay, after that, okay, so now they have reduced the battery size. Okay, so now the battery which they have in their EV, it can able to give only 200 volt, but the motor requires a 500 volt. So what they have done is they have included a DC to DC converter, like a boost converter, to boost the voltage. So it can able to deliver a 500 volt. Okay, so this is one of the case scenario where this power converter will come into a picture for EV. One is to reduce the battery size. Okay, like if we want a more voltage, if you want a more voltage, instead of going with a more number of battery cells, what we can do is we can reduce the number of battery cells and we can boost the voltage using boost converter. Okay, so this is one scenario. Okay, and the second scenario is, we know in EV, okay, for storage purposes we are going to use battery. Okay, so either it could be a lithium ion battery or lead acid battery, and currently they are working on a super capacitor also. Okay, but all this storage, right, it can able to store only a DC power. Okay, all this power storage equipments, right, it can able to store only a DC power, but the motor whatever they are using in an EV, right, it will be an AC. Okay, so what we supposed to do is we have to convert DC to AC. For that we should have an inverter. Okay, so these are the two case scenarios where this power converter will came into a picture for EV. One is for increasing the output from battery, like by reducing the number of cells in a battery. If you want a more power, right, we don't need to go for a more number of batteries. The reason, it will increase the vehicle weight. Okay, and the second one, to convert DC to AC so that AC motor can drive the EV. Okay, so these are the two case scenarios where this converters comes into a picture. And before we are moving to prototyping, okay, prototyping in the sense the hardware setup, right? So before we will get into this.
சார் எந்த அப்ளிகேஷன் காசு சும்மா பண்ணி தரோம்னா
சரி சார் டெபாசிட் தானே ஆமாம் டெபாசிட் கவர்மெண்ட்டுக்கு தானே
சார் பண்ணால் எங்களுக்கு கிடையாண்ட லைன் வந்து எஸ்டி லைன் பக்கத்துலேயே போகுது. இதை வந்து மாற்றணும், அதுக்கு தனியாக காசு வாங்கலாம் 10,000.
Someone has unmuted, just mute. Yeah, thank you. Yes, so prototyping in the sense before they are implementing in a actual product, they'll test it. Okay, so they test with the hardware, so that can be done with a national instruments. Before that, okay, before prototyping, what we supposed to do is we have to do a simulation. Okay, so there is a sequence before we getting into a product development. First we'll do some research, okay, based on like if we comes to inverter, right, so first we have to decide what kind of inverter we are going to use. Okay, and then components, the rating of the components which we use in an inverter. Okay, once we decided it, we have to run a computer simulation. Okay, so first we have to run a computer simulation, then we have to develop a control algorithms for inverter. Okay, for an inverter we'll be having switches. We have to give a trigger for the switches, right? For that we have to develop a control algorithms. Okay, so the second step will be creating a control algorithm for an inverter, then we'll run the simulation. Okay, once we completed the simulation, we will be moving to a prototyping. Once the prototyping is completed, every test will be going for a final product development. So there will be a flow for developing any product. Okay, so today's class we will be mostly focusing about a simulation. Okay, and the second one you can able to see, yeah, power converter monitoring and control. Control is nothing but controlling the switches. Okay, and the third one, okay, electrical motor drive and control. So even for electrical motor also, so we'll not directly work with an actual motor. Okay, instead initially we'll start with a simulation. Okay, we'll simulate a motor in a system. Okay, like first we'll run PC simulation, then hardware simulation. Finally we'll be getting into the actual hardware. Okay, so I'll tell you about the sequence in the upcoming session, like regarding this electrical machine, right? That is a huge one. Okay, so we'll get into in the afternoon session. Okay, so now we are going to focus about this power converter prototyping. Okay, so when it comes to a power converter prototyping, so this will be the flow. Like we'll be having a battery, like which provides a DC supply. Okay, then we'll be having a load. Okay, it could be an EV or it could be any motor also. Okay, which needs an AC supply. Okay, to do this what we're supposed to have is we need to have a converter. Okay, we need to have an inverter like a DC to AC inverter like the above one. Okay, so we need to have DC to AC inverter, and then we need to have a control algorithm circuit. Okay, so with the help of an inverter and control strategies, we can able to convert from DC to AC. So as I already told you, now we are not going to use an actual component. We are completely going to focus on a simulation. All right. So for circuit design, okay, when it comes to an inverter, it will be a completely an electronic component, right? So to design or to mimic an inverter performance, we are going to use multisim. Okay, so this one, the first, the top picture you can able to see, right? It is in a multisim which will be completely used for a circuit design. Okay, and here in this multisim, we are going to design our inverter circuit. Okay, and the same way, the bottom you can able to see, it is an a lab view environment. In a lab view, we'll be developing a logic for control strategies. Okay, like in an inverter, we'll be having a MOSFET. For a MOSFET, we have to control it, right? Based on the switching only, we are going to convert from DC to AC, right? So the switching algorithm will be developing in a lab view. That will be a separate tool. Okay, multisim is an circuit design tool, and lab view is a development tool which can be used for several applications. Okay, as of now, we are going to use lab view for designing a control strategies for an inverter, but it has so many applications. Okay, as of now we are going to use only for designing and control algorithm. Okay, so this can be replaced, as I already told you, our circuit. Okay, like inverter circuit, right? It can be replaced by multisim model, and the same way control algorithms can be developed using a lab view. Okay, so control algorithms can be developed using a lab view. So first we are going to start with multisim circuit design only. Okay, so later we'll come to a lab view. First we are going to start with inverter circuit design. Okay, and as I already told you, a load. Okay, load, it could be a vehicle, or it could be a motor, or it could be a motor in some equipments also. Okay, it need not to be only EV, it could be any AC load. Okay, so yes, so before I'm getting into the multisim, just I'll show you how exactly this multisim environment looks like. Okay, yeah, actually, yeah, all you people, right, already might have worked on a multisim or some other circuit design tool. Okay, so even multisim will looks like a same environment. Okay, so it's like it is similar like other circuit design environment only. But the advantage of this multisim is after designing your circuit. Okay, think that you have simulated your circuit, and then if you want to test, if you want to test with actual circuit, what we'll do is we'll be designing the actual circuit. For the real circuit, the inputs and output, right, will be given through some other programming language, right? But using multisim, we have an advantage, like with a multisim we can interface hardware also. Okay, so with multisim we can interface a hardware like a data acquisition hardware, or it like a hardware which provides input and which can able to read the output of a circuit. Okay, so with the help of it, what we can do is we can easily compare simulation output and the real world output. Okay, so that is one of the advantage of multisim compared with other circuit design tool. Okay, so once I run my simulation program, what will happen is I'll be getting output for simulation, like the circuit which I have designed, right? So I'll be getting the output for simulated circuit output, and the same way, if I have a proper NI hardware and a real circuit, I'll be getting the output from a real circuit also, and I can able to compare simulation output as well as a real circuit output. Okay, so I can easily compare how exactly it differs from simulation and the real world circuit. Okay, that could be easily done with this multi-sim tool. Okay, and so yes, this will be the major difference between this multi-sim and other circuit design tool. And this multi-sim, right? If you want to develop any control strategies, we'll be using a lab view. Okay, so we'll be using a lab view for generating a control signal for MOSFET. Okay, so in lab view, whatever the program we are going to develop, like the control algorithm program we are going to develop, right? The same program we can be used for real time, like real circuit control also. So this is one more advantage of multi-sim plus LabVIEW. Like usually if you take any other programming language, for simulation we'll be using one tool. Okay, for simulation we'll be using some tool. Okay, and if you want to implement in a real time, from scratch we'll start developing the a program or a logic for a real-time application, right? So that need not to be done when we use this LabVIEW and multi-sim. Okay, because we have to do a very minimal change if you want to convert from simulation to a real time. So there is another advantage when we use this multi-sim and LabVIEW. Okay, so yes, so if you see or if you look into this environment, you can able to see we have an place, okay, where we can take a different components like source, then a basic components, diode, transistors. Okay, so we have an options like, and then we have an option for a basic a copy paste. Okay, and this fourth one, so this is right, this is actually for running a different analysis. Okay, so this part, right, this is actually for running a different analysis like DC sweep analysis, AC sweep, and it will be going on. Okay, like this will totally we have 16 different analysis. Okay, if you want to run any analysis on your circuit, right, we can make use of this. And then we have an option to measure, like it is like a probe. Okay, we can directly connect voltmeter probe or ammeter probe to directly measure voltage, current, or even if you want to measure a power, we have a wattmeter probe. Okay, so we can make use of this to, while running the simulation, if you want to measure a voltage or current at a particular wire, we can make use of it. Okay, then in use list, like if you want, if you are using many components frequently, you can add it over here. We can easily place those components from this in use list. Okay, and this one, this is actually for running your simulation, like run, pass, and stop. And this is the place where we'll be developing or connecting our circuits. Okay, and very important thing, okay, the right side you can able to see few icons, right? All these are desktop instruments. Like if you want to use oscilloscope or if you want to use a function generator, okay, so here we have a different instruments. Okay, also it will be having oscilloscope, function generator, then ammeter, a multimeter. Okay, so what are all the equipments which you use in your college laboratories, right? All those instruments are available here, like simulated instruments. Okay, so all these are simulated instruments. With this we can able to give a variable inputs also, and if you want to view a fine output signal, right, you can make use of an oscilloscope to view it. Okay, in the same way we have so many instruments on a right side. Okay, so in the right side of your multisim window, right, you'll be having so many instruments, whichever you need, right, we can make use of it and we can develop it. Okay, so this is about the environment of a multisim. Okay, so yes, this is one of the circuit for converting from a DC to AC. Okay, but I'm not going to take a very complex circuit. Okay, so as of now I'm going to take a simple DC to AC converter. Okay, and we are going to, like, from the scratch I'll develop the code, and again, when it comes to lab view also, I'm going to develop a control strategy algorithm from scratch, and we are going to run the code. Like we are going to see the working of a simulated circuit. Okay, so for that, I'm not going to use this circuit. Okay, so even this is possible. If we want to develop this, right, it will be taking more time. So I'm not going to use this. We are going to do with a very simple circuit. Okay, so yes, so the last one which I have, whichever I have shown, right, that is a three-phase inverter. Okay, so this one, right, this is actually an three-phase inverter. So I'm not going to use it. Okay, so we are going to design a circuit for a single-phase basic one. Okay, so a single-phase inverter. So here uh, we have used a MOSFET. Okay, so based on this switching terminal, okay, we are going to convert from DC to AC. Okay, and this resistor I have added just as a load. That's it. Okay, so in multisim we are going to design the same circuit. Okay, and then we'll be moving to the next part. Okay, so first we'll start developing a circuit for this multisim. Okay, before that, if you have anything to ask, you can use a chat box, or you can unmute and you can raise your queries. Okay, so fine. Let me directly get into the circuit design. Yes, so this is your multi-sim environment. Okay, so here we have to design our inverter circuit. Okay, so in multi-sim, right, we'll be developing only the electronic circuit. Okay, so first we'll start with source. Okay, so source like a DC source for our inverter. Okay, so to take any components. Okay, so we have a several ways. Okay, the first one is, okay, the first method to place any component is, you can go to place. In the top you can able to see there is an option as place. You can go to components. Okay, place components. Here you will be getting a select a component window. Here you can select the required components. Like we have a different database, master database, in the sense which contains all the components. Okay, and then corporate, in the sense if you want to have a separate component list which you work only in your companies. Okay, in those cases you can go for a corporate database. And if you want to make your own database, right, you can make use of this user database. Okay, so that is up to you. But in a master database we can have all the components. Okay, all the electronic components which is available in multisim. Okay, apart from this, think that there are you need some component which is not available in a multisim. Okay, in that case what you can do is either you can download from internet. Okay, if that component is available in a internet, you can download it. Else we can develop or design our required component also. Even that is possible. Okay, it is not like we can use only the available component. Okay, it is not like that. Okay, if you require some component, and if that component is not available in this database, we can able to create that component. Okay, so just we need to give a specification of the component. Once if we give all the required parameters, right, we can able to simulate a component in a multisim. Okay, even if it is not available in database. Okay, so yes, so here the first one is a database. Always let it be a master database. Okay, and then group. Okay, so in a groups you can able to see different categories like source, basic, diode, like different component categories. Okay, so you can go to the required category and you can choose, or you can make use of your required component. Okay, so now I need a DC input. Okay, it is actually a source, correct? So what I can do is I can go to place component. So here in a group, I can choose sources, okay, and I can choose power source. And as I need a DC power, I can choose DC power and I can place it in my design. Okay, so here you can able to see I have placed my DC source. Okay, think that you don't know like under which category I'll be getting my source. So in those cases, what you can do is you can keep group as all groups. Okay, groups you can give it as all groups. Here in the components, right, you can simply search, okay, DC underscore power. Okay, you can easily search the component and you can place. Okay, anything is possible. Okay, you can go for any one of this method. Okay, so this is one of the way to choose a component, like choosing a power. Okay, and the another method is here you can able to see there is a shortcut for directly getting into a place source window. Okay, if you want to place a source, you can directly click basic. In the sense, it will be having a resistor, a capacitor, those components. Okay, then we have a diode, a transistor. Okay, so here we will be having a separate button for every groups. Okay, so we'll be having a separate button for every group. If you know your components belongs to this group, right, you can directly click on this and you can get the components. Okay, so even this is also even in this way you can able to place a component. Okay, so now we have kept a source. Next, we need to take a transistor. Okay, the transistor which we used is IRF 3205. All right. So what I can do is I can go to place component. Instead of searching the component, I can directly type the name. Okay, so IRF 3205. Okay, I can directly click and I'll place it over here. Okay, so here you'll be having its information. Okay, so I have taken a MOSFET. So totally we need 4 MOSFET. Okay, so I can use a shortcut Control C, Control V to create a copy of it. So just I have created a copy and I have placed it over here. Okay, so now I can give the connection. So now I'm not going to use the capacitor. So those capacitors just for filter, right? So I'm not going to have any filters. So I'm going to design without a filter. Okay, so it's just I'll give the connection. Okay, so I have given this connections. Okay, so just I'll move this. Yes, so I have my source, then I have taken my 4 MOSFET. Okay, so next what I'm supposed to do is I have to add a load. Okay, I have to add a load. So here I'm going to use a resistor. Okay, so I can go to basic or resistor. I'm going to use 100 ohm. So let me take, just I'll type it as 100 and I can place it over here. Okay, so now I have to give a connection, like one end of the resistor should connect between these 2 MOSFET and another end of the resistor should be connect between these 2 MOSFET. Okay, so but as of now you can able to see both terminals are in line, right? So to rotate the component, okay, so either you can go with menu or you can use a shortcut. So if you want to go with the menu, just right click on the component. You have an option called rotate 90-degree clockwise or 90-degree anti-clockwise, and we have an option for flip also, flip horizontal and flip vertical. Okay, you can make use of can make any of this option to rotate as per your requirement. Okay, So now I'll just use rotate 90-degree clockwise. So yes, so now I can give a connection. Okay, so this end I'll connect between these two MOSFET pair. Okay, and this one I'm going to connect between these two MOSFET, that is Q3 and Q4. Okay, so yes, so the output voltage, right, we have to measure parallel to this resistor. Okay, so the output of this circuit, right, we have to measure parallel to this resistor. And yes, our input is a 12 volt DC, and this is an inverter circuit, and output we should get as AC. Okay, so output we should get as AC. So to get output from this circuit, I must have to give input for my MOSFET. Okay, so I have to give input for my MOSFET. Only then I can able to get an AC output. Okay, so we know, right? So we have to turn on each MOSFET at a particular time, like a regular interval. I have to turn on and turn off each MOSFET pair. So in this, Q1 and Q4 is one pair, and Q2 and Q3 is another pair. Okay, so here what we're supposed to do is I have to give input for my MOSFET. Okay, so I have to give input for my MOSFET based on the gate input. Based on the gate input only, we are going to convert from DC to AC, right? So I don't want to explain the working of the circuit, as you all know how exactly it will work. Like when these two Q1 and Q4 are enabled, okay, when Q1 and Q4 are enabled, our voltage will flow like this. Like first it will go to Q1, then it will go to the load. So when Q1 and Q4 are enabled, our voltage flow will be downwards, which corresponds to load. Okay, like from Q1, then it will go to R1, the flow will be like downwards, then it will go to Q4 and it will close the circuit. Okay, the flow will be like downwards, which corresponds to low. Okay, when Q3 and Q2 are enabled, okay, when Q3 and Q2 are enabled, better I can show with slide. Okay, I can take a pen and let me just change the color. Okay, when these two are enabled, Q3 and Q2 are enabled, our flow will be like this. Okay, so it will come to Q3. Okay, then the flow will be like upwards direction. Okay, the flow will be like upwards direction, and then it will close the circuit. Okay, so when Q1 and Q4 are enabled, we'll be getting the positive cycle voltage. Okay, we'll be getting a positive cycle voltage of AC. Okay, when Q3 and Q2 are enabled, we'll be getting negative cycle voltage of an AC. Okay, so we are converting from a DC to DC by switching switching each pair of a MOSFET. Okay, so here to measure the voltage, what we are doing is we are measuring a voltage. Sorry, we are measuring a voltage at 2 points. Okay, so here as well as here. Okay, we are measuring a voltage at 2 points, and if we calculate the potential difference, like the difference between these two voltages, right, we'll be getting the final output. Okay, by calculating a voltage difference, by calculating the potential difference between these 2 points, we can easily calculate the output voltage. Okay, if you want me to make it in a simple way, think that I'm connecting. Okay, let us consider I'm connecting an oscilloscope. Okay, in an oscilloscope, if plus terminal, if I connect here, okay, minus, and if I connect here, okay, so what happens is Q1 and Q4, okay, Q1 and Q4, when it is turned on, our voltage will come as an output, right? When I connect like this, plus in the top and minus in the bottom, Q1 and Q4 will be considered as positive of cycle, and Q3 and Q2 will be considered as negative of cycle. If I connect in a reverse way, like bottom if I connect plus, and in the top if I connect the minus terminal, in that case Q1 and Q4 will be turned on, will give a negative of cycle. When Q2 and Q3 are turned on, it will be giving a positive of cycle. It is completely based on how we connect the terminals. Okay, in the same way, if I subtract V1 from V2, okay, so when we do this, our Q1 and Q4 will be considered as positive of cycle. Okay, if I do the reverse, V2 minus V1, in this case Q2 and Q3 will be considered for positive of cycle. Okay, it is completely based on how we connect. When it comes to real time, how we connect the terminals in a simulation, the parameters which we subtract. Okay, so that's it. And this is the working of this circuit. Okay, so now we can directly get back to our design. Okay, so in this you can able to see in a multisim we have completed designing our circuit. Okay, so circuit design is over. Okay, now the thing is I have to give input for a gate terminal of my MOSFET. Okay, so that is the very important thing when it comes to an inverter. Okay, this gate signal, right, that decides your output signal. Okay, so the gate signals, right, the gate input, right, that decides the output of our inverter. Okay, so that takes a major role when it comes to an inverter, because based on the signal which we provide, the output signal varies. Okay, the output signal will vary. Okay, so here the thing is, as we are going to see, okay, different control strategies. Yes, with this a single circuit. Okay, with this single circuit we are going to see a different control strategies for MOSFET, and we are going to see the response of the circuit for different control strategies. Okay, so with multisim, okay, with multisim we can't provide enough input. Okay, so we can give an input, like we can keep some PWM signal, and we can provide an input, we can able to see the output. Okay, but that will not be much interactive to your circuit. So what we can do is all these inputs. Okay, so inputs for all this MOSFET, right, I'm going to provide from LabVIEW. Okay, input for a MOSFET gate terminal I'm going to provide from LabVIEW, and the same way output of the circuit. Okay, the output response of the circuit also we are going to monitor from LabVIEW. Okay, so just try to understand multisim. Whatever we have done is just we have designed the circuit, simulated circuit, but the response of the circuit we are going to see in LabVIEW only. Okay, so before that I need to specify, okay, in this in multisim itself, I need to specify what are the inputs I'm going to provide from LabVIEW and what are the response I have to see from this circuit. Okay, so in this, okay, in this circuit we know that I want to control a MOSFET, a gate terminal, correct? So totally we have a 4 MOSFET. In this case I have to provide 4 inputs from LabVIEW, correct? So in this case we easily get to know I have to provide 4 inputs from LabVIEW for 4 MOSFETs gate terminal. Okay, so to provide an input or to create a reference for those input, what we're supposed to do is we have to create a connectors. Okay, so we have to place in a simple way, if you want me to say now a layman term. Okay, so we have to place some component. Okay, so we have to place some component which links multisim and LabVIEW. That's it. Okay, so if you want me to say in a very simple way, we are going to add some component like some icon. Okay, we are going to place some icon which links multisim and LabVIEW. Okay, so we'll see what exactly that a component is. Okay, so if you go to place, okay, here we'll be having an option called a connector. Okay, so here we'll be having an option called connector, and you can able to identify two connectors like input connector and output connector. Okay, in this input connector, right, it will be used to provide input from LabVIEW. Okay, so if you want to give any input from LabVIEW, we have to use input connector. In LabVIEW, if you want to see something, if you want to see the response of the circuit in LabVIEW, in that case, we'll be using an output connector. Okay, so in our case, we need 4 input connectors for 4 MOSFET gate terminal, and then 2 output connectors to measure voltage at 2 different points. Okay, so first we'll connect, or we give a connection for a MOSFET gate terminals. Okay, so I'm going to click on input connector. I'll be placing over here, and these names, right, we can give a name like a user defined name we can provide. Okay, so I'm going to put it as S1. Okay, so for this I'm going to put it as S1, and again just a basic copy paste, control C, connect this, then control C, control V. So let this be 2. Okay, again I can change its name as S2. Again control V, S3. Okay, so I'll just double tap and I can give a name as S4. Okay, so I have placed all the components. Okay, all the connectors, not a component, all these are connectors. All I have placed all input connectors for MOSFET. Okay, so next I need to measure voltage between this resistor, right? So if you want to measure and if you want to see in LabVIEW, we need an output connector. So I'll go to place, connector, output. Okay, I can just place it over here. Here I can put it as V1. Okay, better I'll put it as old 1. The reason why it not created is our source name, right? It is already specified as V1. That is the reason. Okay. This one I will put it as old 2. Okay, so I have taken 2 output connectors to measure potential difference between a resistor. Okay. Yes. So now we have completed a multisim part. Okay. So sorry, I have not connected this. Yeah. So now you can able to see I have completed the multisim part. Okay. Circuit design is over, and to provide input and output, we have placed input and output connectors. Okay. So now what we need to do is just we need to save this design. So I'll go to file, then I'll choose save as. I'll save it in desktop. Okay, so desktop, I'll just put it as EV, and I can save it as PC2 AC. Okay, I can just save this circuit. Okay, so we have completed designing our multisim part. Okay, now to provide this input and to see the output, we have to go for a LabVIEW. Before that, okay, before that, we'll see what are the different control strategies we can provide for this circuit. Okay, so yes, let me just come back to the slide. Okay, so we have completed this part, multisim part. So this is your LabVIEW part. Okay, so this is your LabVIEW code. before that, okay, from lab view, we are going to provide 3 different control strategies. Okay, from lab view, we are going to provide 3 different control strategies. The first one is square wave. Okay, the trigger pulse, right? We are going to provide a square wave. It is like when Q1 and Q4 is on. Okay, when Q1 and Q4 is on, we'll make Q2 and Q3 to turn off. Okay, when Q2 and Q3 is on, Q1 and Q4 will be off. Okay, so we are going to provide alternate on and off signal for our MOSFET pack. Okay, if we do this, okay, if we provide the signal to our circuit, output will come as square wave. Okay, output will come as a square wave. So now you people might think AC signal should be a sine. Okay, actually it need not to be sine. Okay, a sine is not only an AC signal. This square, triangle, sawtooth, okay, all these signals are AC signal only, which amplitude value varies with time. Okay, so all these are AC signal, and the same way a square wave also can drive a motor. Okay, so square wave also can drive a motor, but the problem is the efficiency of the motor, right? It will not be good when we use a square wave as an input. Okay, square signal as an input. Okay, the very basic simple control strategy is square wave. Okay, and the second one, we are going to try modified sine wave. Okay, modified sine wave. So to do this, we'll be using a 2 square wave with 90-degree phase shift. Okay, with that we'll be getting this modified sine wave. Okay, and the third control strategy is SPWM signal. Okay, so in all these 3 methods, okay, in all these 3 methods, our circuit is gonna be the same. Okay, we are not gonna do any changes in our circuit, but the input for our circuit, like the input signal for our MOSFET gate terminal, right, will be doing a very minimal changes. Okay, we'll be doing very small changes in the control strategies, like the input for our gate signal. Based on that, just we are going to see the response of our circuit. Okay, so we are going to start with square wave, a very basic one. Then we'll be moving to a next one. Okay, each one by one. Okay, so yes, when we use a square wave, this is how the output will be getting from a circuit. And when we use a modified sine wave, so this is the output which we get. And when we use a SPWM, right, this is the output we get. And yeah, you all know about this SPWM, like this will be considered as positive off cycle. In this, when the amplitude is very minimum, the duty cycle of this PWM, right, it will be very less. Okay, once it reaches high, okay, the duty cycle of this PWM will be maximum. Okay, which means when it is here, okay, at this point, off time will be high, on time will be less. Okay, once it reaches peak, okay, once it reaches peak, at this point, our on time will be high, off time will be less. Okay, so that is how your SPWM signal will, that is the characteristics of your SPWM signal. Okay, so even SPWM signal can be used for driving a motor. Okay, so yes, so now we'll just see how we can get, or how we can see the response of our inverter in lab view. Okay, so I'm just going to open a lab view. So I'm going to create a new program. Okay, so I have created a new programming environment. Okay, so in the morning session, I hope Raj has explained the environment about lab view, so I can directly pitch into the programming part. Okay, so now we are going to do a simulation, as we both know. Okay, so we all know we are going to do a simulation part. Okay, so this, as I already told you, lab view is not only meant for a simulation. It has so many features. Okay, so this tool, right, it can be used for image based application, for image processing application. Okay, it can be used for a data acquisition application, can be used for IoT or serial communication. Okay, so its use areas are huge. Okay, it can be used for biomedical. Okay, it is not only meant for simulation. Okay, so it has so many key areas. So this window, right, this block diagram window, we know we are going to use for a programming part. But when it comes to simulation, okay, when it comes to simulation, I can't use this window directly. Okay, I can't able to make use of this window directly. Why? Because this is right, this window, right, it has several use cases. First, what I supposed to do is I want to make this programming environment for simulation. Okay, first I need to make this program, this VA, for simulation environment. Okay, only then I can use for simulation. Okay, I'll tell you why. Okay, so first, as you know, I have already told you, like, we are going to communicate multisim and LabVIEW, right? So first I need to access a multisim in LabVIEW. Okay, so to do that, I'll just right click. I'm going to control and simulation. Okay, external model, multisim design. Okay, this is the function. Okay, so this is the function which will be used to access multisim circuit in LabVIEW. Okay, so this is the block which will help me to access multisim design in LabVIEW. Okay, if I try to place this block, okay, if I try to place this block, you can able to see I'm getting a block icon. Okay, I'm getting a block icon. The reason is I have not changed my LabVIEW environment to one simulation environment. Okay, that is the reason I'm getting this block icon. Okay, as I already told you, LabVIEW has several use cases. Okay, it is not only meant for a simulation. Okay, so that is the reason if you try to place the block, you are getting a block icon. First, we need to make a LabVIEW to work for simulation. So what I have to do is I have to right click, control and simulation. Here you can able to find control and simulation loop. Okay, you can able to find control and simulation loop. Using this loop, we can create a simulated environment. So I can just take and I can drag and I can place my control and simulation loop. So inside this loop, okay, inside this loop, whatever block we are going to place, right, it will be a simulated block. Okay, so it is like a simulated one. Okay, so the outside one, it can be used for some real-time applications. Okay, so now inside the simulation block, now I'll try to place my multisim design. I'll just right click, I'll go to control and simulation, external model and multisim design. Okay, so even now if I place my mouse in the white background, okay, like that is your actual block diagram. Okay, if I try to place my mouse over the block diagram, right, I'll be getting a block icon. But once I move my mouse into this control and simulation loop, you can able to see I have an option to place it. Okay, all your simulated block can be placed only inside a control and simulation loop. Okay, we can't directly place in a block diagram. Okay, first, if you want to perform a simulation, first we have to create a simulation environment. Inside that simulation environment only we can do all our required process. Okay, so here I have placed a control and simulation loop. Here I can place my multisim design block. Okay, so I'll just place it over here. Once I place my multisim design block, it will give me a pop-up, okay, to choose my multisim design. Okay, as we know, we are going to call our multisim program, right? So here I need to specify which multisim design I'm going to call. Okay, so I'll just use a browse option. and I have saved it on desktop EV. Here I have my multi-sim design. So okay, I have given us DV. Okay, so just I can change it. Yeah, I just renamed it. Okay, now I have selected my multi-sim design. I'll just click OK. So once I have clicked OK, you can able to see it has some terminals. Okay, it created with some terminals, like you can able to see names are S1, S2, S3, S4 and voltage 1 and voltage 2. Okay, these are the names which I have provided for input connectors and output connectors. Okay, so these are the terminals. Okay, like the names which I have got, which I have provided for all inputs and output connectors. Okay, so now for your understanding purpose, okay, only for your understanding purpose, okay, I'm going to take one more connector. Like let me take one output connector. Okay, I'm going to take an output connector. Just I'm going to connect it over here. Okay, I'm going to connect it over here, and this name I'll put it as output new. Okay, I have given a name as output new. Just I'll click OK, and I need to save this file. Okay, so now in my multi-sim I have added a new connector. Okay, now we'll get back to lab view. Okay, so as I have made a change, I have to refresh it. Okay, I'll just right click. I'm going to refresh my multi-sim design. Once I refresh this, second, whether I have saved it. Okay, so sorry, this has been named as DV2 AC. Just I'll change this. Okay, so DC to AC, save. Yes, okay, the name is the problem. Okay, so now I have saved as DC to AC. Now I can refresh it. Okay, so now if I refresh, you can able to see one new terminal is been created as output new. Okay, so in your multi-sim design block, okay, in LabVIEW, if you place a multi-sim design block, the input and output terminals, right, it is completely depend on the input and output connector which you placed in your multi-sim design. Okay, if I delete this, okay, now I'm going to delete the extra one. Okay, I'll be just saving it. Okay, now I'll get back to LabVIEW. If I refresh this, okay, so now if I refresh my multi-sim design, the extra terminal I have removed from my multi-sim, so it removed on my LabVIEW also. Okay, so the terminals in your multi-sim design block, it's completely based on input and output connector which you placed in your multi-sim program. Okay, so multi-sim design. Okay, so yes, we have taken or we have successfully connected or related multi-sim and LabVIEW. Okay, so in this, first what we supposed to do is I have to give input for my switches, okay, for my MOSFET gate terminal, and I have to see my output, right? So to see the output, it is a very simple one. Okay, so what I supposed to do is I have to find the potential difference. So potential difference is nothing but a difference between the voltage at 2 point, right? So I'm going to take a subtract function and I'm going to subtract these two voltages. Okay. Then if you want to see in a waveform graph or a chart, so even here we need to use simulated graph only. So I'll just right click. I'll go to control and simulation. Simulation, a graph utilities, I'm going to use simulated waveform. Okay, so here I'll be getting my output of my circuit. Okay, so here I can see the output response of my circuit. Okay, so now the pending thing is I have to give input. Okay, the thing which we kept pending is I have to give an input. So input, as I already told you, at a particular time we have to enable only a single MOSFET pair, right? So to do that, it is simple way to go with a square wave. So I'll right click. I'm going to control and simulation, signal generation. We have signal generator. Okay, so as of now, you can able to see there is no input. Okay, for this signal generator, you can able to see as of now there is no input, which means we have to configure only. Okay, I'll just double tap. I can go inside. First, I'm going to choose a signal type. Okay, signal type, I'm going to choose it as square, and amplitude, let me specify amplitude as around 15. Okay, and frequency, okay, frequency I'm not gonna configure here. Okay, instead I'm going to have a terminal for it. Okay, as of now it is selected as configure dialog box, right? I'm going to change it as terminal. So as I have changed it as terminal, I'll be having a terminal for frequency. Okay, so I'll be having a terminal for frequency. So in a front panel, what I can do is I can take a knob which will act as a frequency for my square pulse. Okay, this I can connect it over here. Okay, so just a simple thing. Okay, so for my square pulse, okay, I'm going to control only the frequency. Okay, apart from frequency, remaining all are configured inside. Okay, leave about this value, it will not take this value. The reason we have a control to control the frequency of my square pulse. Okay, so the next step is, okay, so just a minute. Yeah, so the next step is we have to give, based on the square pulse, we have to give input for our switches. Okay, so let me show you how to do that. Okay, so we have to develop some logic. Okay, when the square pulse is positive, okay, when the square pulse value is positive, I have to turn on S1 and S4. When it is negative, I have to turn on S2 and S3. So I'm going to use a simple comparison logic. I'm going to take a greater than function. Okay, and I'm going to check whether this value is greater than 0. Okay, I'm going to check whether my square pulse value is greater than 0. If, okay, if my square pulse value is greater than 0, I'm going to add a logic. Okay, if this value is 0, okay, I have to pass my square pulse signal, okay, my reference signal, but here I'm going to use absolute value. Okay, I'll tell you why I'm using this absolute value later. Okay, so the use of this absolute value is it will make a negative value also to a positive value. So that is the use case of this absolute value. Okay, if my square pulse value is 0, I'm passing my positive off cycle. Okay, if this condition not satisfies, if the value is negative, I'm going to pass 0 voltage to my gate terminal of S1 and S4. As you know, S1 and S4 are one MOSFET pack. Okay, in the same way, I'm going to have another condition, like I'm going to use a less than function. Okay, and I'll be checking whether my square pulse value is less than 0. Okay, the same condition replaces. Okay, if it is less than 0, I'll be passing my square pulse value, else I'll be passing a 0 to switch 2 and switch 3. Okay, like MOSFET 2 and MOSFET 3. Okay, we have completed everything. Okay, and few configuration is pending. Okay, as we use this control and simulation loop, we have to do few configuration. Like if you double tap on this, the configuration you can able to see like a timing, how long we have to run this simulation. As of now, it is configured as it has to start from 0th second and it has to end at 10th second, right? So it means after 10 seconds, our simulation will stop. Okay, I don't want to stop after 10 seconds. I want to run the simulation until I press stop. So what I can do is, in the time, I can put it as infinite. INF, which indicates infinite, which means my program, my simulation will run indefinitely. Okay, so this should be the first change I have to do. And the second change is, now there is nothing to control my loop, right? So I have to add some function which controls the loop. Like I can control when I have to stop the simulation. To do that, I'm going to control and simulation, a simulation, utilities, halt simulation. Okay, I'll be using halt simulation. For this, I'm going to create a control. Okay, input. Okay, create, sorry, it is not coming properly. Yeah, create control. Okay, so just keep this in mind. Okay, in LabVIEW, we are developed a logic. Okay, we developed a logic to provide a signal for a MOSFET gate terminal, and that signal is going to this block. Okay, the control signals, right? It is going to this block. This block will call multisim and it will provide this value. Okay, after that, from this block, we are measuring the output voltage and we are going to visualize in a waveform chart. Okay, so just we'll run this. Okay, and keep this in mind. Okay, the input for our signal is DC. Okay, so let me just run this and we'll see the response. Okay, so as it is a simulation, initially it will take some time to run. Okay, and I'll enable the auto scale. Okay, you can actually, the frequency value I have provided a very minimal value. I can just increase it. Okay, I can increase the frequency. So now I have provided some 10 at something. Okay, so even if I increase, you can able to see the change in on and off time. Okay, even if I increase even more, okay, I can able to decide the frequency. Okay, you can able to decide the frequency of my square pulse with the help of our reference signal. Okay, so here actually we are changing the switching time, like how fast we switch between a MOSFET pair, right? That actually we are deciding here. Okay, so this is one of the control strategy for our single phase inverter, which provides a square output. Okay, square as an output of an inverter. Okay, in the same way, we have few more strategies. Okay, so that I hope we can see after a lunch. Okay, after break. Okay, so before that, if people have anything to ask with respect to this program, you can ask now. Else, we can able to see after break and we can go for break. Okay, if you have anything to ask, you can ask. Okay, so yeah, so thank you, Mita. Okay, so S3 I have connected now. Okay.
Sir?
Yeah, yes, ma'am.
Okay, sir. Shall we continue in the next session, sir, by 2 o'clock?
Yeah, yes, ma'am. Sure. Thank you.
Okay, sir. Thank you.
And whether